Jarek, welcome
Nice to meet
back.
you. Hi.
Hello. Hope you had some time to rest after the first talk and you are ready to inspire people with functional programming and assembly during the next hour.
Okay, yeah, I am ready.
Okay, let's start then.
Okay, hello. So it's now a second session of mine today. It's a great pleasure for me. Although I still say, I must accent, I would rather be in Kiev doing that talk and talking to all the people directly, but it's okay. The life is as it is now. So an hour ago, I was talking about monads, function composition, and stuff like that. And this is very far away from metal. However, if you join a functional programming community, you will see that tons of people are actually deeply interested in assembly, in the low-level stuff. And that's not accident. It's not that we want to only do higher abstractions and totally forget about the machines. We sometimes cannot forget about them. We would like to forget, but yeah. I will show you why so many functional programmers actually are interested. So, my name is Jarek, maybe now a little bit. I started with Commodore 64, and then I was doing some Amiga with assembly and C. Then I switched to C++, and then suddenly came Java, JavaScript, recently more Kotlin. I work for engineers doing consulting for banks, insurances, and such companies in Switzerland. So, a lot of Swiss ranks, I like it. Okay, so motivation for this talk is more or less this mythical slow solution. Sometimes, and I think many people of you have seen that, you present some piece of code and then someone says to you, oh, isn't it slow? Oh, this would be slow. And then you wonder why it's even important thing here to talk about it. And then for sure, as a developer, younger or more experienced, you've seen tons of statements about performance of some constructs in a language. This is slow, this is fast. Streams are slow, for loops are fast. Yeah, that kind of. And as a developer with, now, is it for 30 years, almost 30 years of experience, starting from basic, I have seen these statements from the beginning, like basic is slow, this in basic is slow, like this construct, or C language is slow. I still remember when I was writing code for Amiga that writing a C code was considered to be writing in a higher level language that is incredibly slow compared to assembly. And I even remember this moment when someone was showing me that post-incrementation is slower than pre-incrementation. And obviously I should always use pre-incrementation. There is such thing. Or the collections are slow in C++. Or Java is slow. Object-oriented programming is slow. Functional programming is slow. And all that stuff. Or monad transformers are slow, if you are into monads. Okay, is it all true? And in this talk, I'm going to explore this kind of statement. It's like, I'm not answering these questions directly, but I will show you the tools and some things to think about whenever you are faced with such statements. Long time ago, life was simple. That is a piece of the code maybe I was writing exactly 30 years ago. Fibonacci in assembly on Commodore 64. Yeah, that's a very primitive version. And I remember from a book that I even still have this book. It's now barely readable. That there is this branch if equal. So if something is equal, you jump. That if the branch is taken, so if it's true, it takes 3 cycles. If it's not taken, so it goes to the next instruction is 2 cycles. And the branch basically in an assembly is either you do a loop, for loop or kind of looping, so you can't do much, or you do if statement with a branching. If it's if statement, then maybe sometimes you just can rewrite this if statement in a way that instead of doing these 3 cycles, you can do 2 cycles, just you negate the condition. And I remember the time, and it was like piece of art to actually rewrite if statements, like logically if statements from assembly, in a way that they take less cycles. And it was like challenge. Absolutely for nothing, because I can tell honestly, almost 100% of the code I was writing back then had absolutely no problems with performance. Okay, if it had, this one cycle wouldn't even fix it. But yeah, that was nothing, critical for millions of people. They were just stupid games that, okay, worked more or less. Yeah. So now more funny, this behavior, I continue even on my Amiga, and it was like, higher school of coding to do branch smart. But then came new Motorola. I never had this CPU, but I read about this CPU like beginning of 90s, and then I realized something in the description that, contrary to all the previous version of this CPU, now if you jump with a branch with conditional, it's actually faster than not jumping. Which means all this handcrafted assembly code, like hundreds or thousands, I don't know, developers were writing in the past, is now even slower than just regular simple code people write. How funny is that? Because we were just targeting specific machines, specific version, and now people having better machines that actually maybe they exactly want to have as fast possible application as fast application as possible. They actually slowed down by us to be a little bit too smart. Yeah. Well, Motorola, you're such a troll. Yeah. And that's how I more or less learned that the premature optimization is, the root of all evil. Yeah. So the problem, performance myths, the statements that people spread in network, social media, between colleagues, that not really are not typically precise. If they are valid in certain contexts. Maybe they were exactly valid in the past. That lots of performance myths about these things that were true in 90s in simple computers, but that are not true anymore now. Or that's even the most important thing. If they are true, they are absolutely not relevant to the observable performance of your project, of your application. Yeah. So, and there is a big cost of this performance myth. Rarely it makes that, what I showed, that you wanted to craft a faster code and you ended with actually slower. Mostly what happens that people prefer less readable solutions, or less flexible, less abstract, just in order to win mythical CPU cycles that not actually are there. And developers lose focus. They focus on this, performance tricks, or just not using good abstractions, just writing, simple code, and with the possibility that this will perform faster. Yeah, and they just cannot really use their full skills as a developers. And there is a reason for that, why this is like, no one is particularly evil, but we as a humans, we love numbers. So performance benchmarks are really cool thing to market anything, to compare stuff, because how can you compare, is this code more clean or is more readable? This is really hard task, and actually quite often I'm involved in such discussion. This is code better, and you have no good measures for that. Okay, there are some, but none of them like fully acceptable. But when it comes to benchmarks, you just show the numbers. Okay, my code is like this, but I'm 3% faster, and now it sells. It sells because you show the number. So to the point that maybe a lot of you want to state now, so is functional programming really producing a slow code? Because that's something probably most of you have heard and some of you believe. And maybe that's even true. So I actually, this talk initially I did for Scala, and I heard, I found many articles about performance of Scala collections and monads and things like that. I adapted this to be a little bit more Java oriented. In some pieces of examples, there will be Scala written, but it doesn't really matter. It's the same about Scala or Kotlin or any language. Yeah? And the main example I have rewritten to Java to be more familiar to regular developer. Okay, the problem is when we talk about performance on the JVM, that's not an easy thing. So you have in Scala here, think for a moment, you have Java or whatever language that works on JVM you can have, right? And we have this code, and this code is compiled to bytecode by Scala C, Java C, whatever, Kotlin compiler. And this bytecode looks more or less like assembly, but it's not assembly. It works on the JVM runs it. And this JVM is not a simple thing. It's a machine that has complex stuff inside, compilers, GC particularly, so garbage collector, and it's not really interpreting, contrary to what tons of people believe. It's not really interpreting. It's sometimes interpreting this code and then finally really perform some assembly instruction. But for any critical part, it's actually compiling it by different, more and more aggressive compilers to the assembly pieces of assembly code, which finally are executed on the CPU. And the CPUs that we have now are not the CPUs that we had in 90s, like 386, 380, or even this Amiga. They are very complex. They have this multiple level of caches, speculations, etc. So those are complex machines. And to make this picture even more complex, there is OS, that operating system that basically touches and changes all this stuff, how they work. Like you don't exclusively have CPU, JVM. It's not the only thing you have to take into consideration, because JVM on different operating system will behave differently, etc., etc. So analyzing that, making statements how the code would perform on this complex picture is actually hard, because all of these elements can change something. Yeah. So the given piece of code, if you put in isolation, can perform completely differently when used in a little bit different context. Like the code around is different, the operating system is different, the JVM is different, etc., etc. And that happens. So in this presentation, we'll go deep from a very simple piece of code, but we'll go deep from that. And this presentation is not about putting you some benchmarks, because benchmarks are lies. It's not about presenting you the numbers, but about showing you the tools that you can check those numbers on your own, because that's important. If you know how to validate these statements, you can in the future be ready for discussions, for real discussions. You can validate if someone is lying. You can take a benchmark and maybe see that it's actually not really correctly written, etc., etc. My statement is, unfortunately, I would say all the benchmarks are lies. Some are bigger lies, some are smaller lies, but they are lies. And they, quite often when I look at my benchmark from the past, no matter how many even weeks I spent to make the fair benchmark, after I learn some things in a year or two, I learn this wasn't really fair benchmark. That's reality. Yeah. That's also a sad story, because somehow there is no good. There's no. I don't really know how to write perfectly fair benchmarks, but I will show you how to spot imperfections. So let's talk about immutability. That is step number 1 in functional programming, and a lot of developers believe that immutability makes you slower. And there is a lot on that topic, but I will show something which is simple but extreme. Let's imagine Imu Table Calculator. So actually, it's kind of symmetric. So you have a private property total. You start a calculator with, for instance, 0, and then you have method add, which creates a new calculator, but with a little bit different changed accumulator, this total, added some value. And then you have just additional method get to extract the value. There is like immutable calculator. How cool. Contrary to that, mutable calculator is very simple. Method add returns void. Void is something in the functional programming that we hate. How can something be void? It's just a reason for all the mistakes people do. We'll never do something void. But yeah, if we do void, then we actually can have potentially faster calculator. Is it faster? Let's measure that. So the measurements starts with writing code for measurements. Maybe we care, and now for this presentation, we concentrate on how much time does it cost, how much CPU. So a lot of people, and I find it even now, will write measurement this way, like immutable calculator, start nano time, do some addition, and then print the style. That is how you not write any actually benchmark, not only in Java, but especially in Java on the JVM, but not even in C++ or whatever languages. In all the other languages, like which are statically compiled, this leads to less errors, but still to some errors. In Java, this is totally broken on the JVM. This brings you number that mean absolutely nothing. So what is the point? In JVM, actually, and most of have this just-in-time compilation, and the idea is that most of the code is not time critical. So maybe let's concentrate and aggressively compile only these pieces of code which do matter. Which pieces of code matter? Those that are called often. So we can rewrite benchmark in a way that we simulate that we often call this piece of code, like maybe 10,000 times. And after we do that, there is a hope compile JVM will understand, oh, this is a hot thing. That's, by the way, hence the name hotspot we sometimes use, yeah? And if it's hot, then maybe we'll start measuring and they will print. And this time, this will be a little bit better. The numbers that will be presented here are a little bit better. And I won't show you because it doesn't really matter. It's still not cool. What we can do, you can actually validate if just-in-time compiler in JVM works. There is this flag, print compilation, which prints you more or less something like this. And it says, yeah, Imu Table Calculator was like init, that means constructor, then add. And what is this tree here? It means that the level 3 of compilation was basically done here. Then here was level 4. It means more aggressive, more or less means the higher the number, the more aggressive compilation went here. But what is important, here it is a println statement from the code. It means that actually this end of warm-up was after all this compilation have taken place. Which means, more or less, could be that we measured the code that was actually made as fast as possible by the JVM. So maybe we are measuring something at the actually optimized level, which is good. But the best option is not to write this kind of measurements on your own, because there are more problems to consider, tons of problems, and I don't have time to even cover them. But it's best to use a tool with a documentation which describes typical pitfalls. And this Java micro benchmark harness, that's the tool. So it takes care for you about JVM warm-up. And if you look at the documentation, which will tell you how to, for instance, prevent something known as dead code elimination. So sometimes when you, I will show you an example, yeah? And it has documentation that covers a lot of potential problems. So if you use JMH and you read the documentation, there is a huge chance that your benchmark that you will write might have sense. There are additionally, I don't know how many, but many examples to JMH inside of the project that you can take a look, and they will show you how to test typical stuff. So that's how the testing code would look in benchmark. And for instance, important piece of code here is this black hole. Black hole, whenever I calculate, at the end, I send my results to black hole. Hadn't I do that, had I forgotten about it, what could have happened is that there is an optimization in JVM that says if no one actually cares about calculation, then we don't have to do them. So then it can happen then that your benchmark shows incredible good numbers. If it's so, think that maybe you haven't used a black hole and JVM has totally optimized your call. It means nothing is actually working here. Yeah, so you're having good numbers because you calculate something that was completely like commented by compiler. So here we have two examples of Imu Table calculation test, Imu Table more or less in the same numbers. One important thing is when you do benchmark, you have to wait for your benchmark. If benchmark takes less than a second, it means there's a huge probability that you are measuring some accidental spikes done by your operating system, etc. So you have to wait sometimes minutes for your benchmark to be sure that it shows something that it's repetitive. that at least the numbers are not accidental. So now going back to this code, I hope you remember this immutable calculator, mutable. What you think will be faster? When we run it on an OpenJDK 1.8, will be difference visible or not? And that's a good question. Answer to that is, when I do this test, and by the way, this benchmark is somewhere on a GitHub. I hope I have here link. If not, I can share it later. Immutable calculation test actually was almost 10 times slower than mutable. So it would say, oh, mutability costs a lot. But now some of you may think, okay, I explicitly put here a number 1.8. Maybe a newer JVM is better in that. Is it? So, well, maybe we'll see, yeah? Maybe version 15. And if you look at it, kind of not really. It's not really that it matters, this change that we see here. Yeah, a couple of percents better. I think it's accidental. By the way, those numbers here were taken unprofessionally. Like, I didn't want it to wait incredible amount of time to have a really proper benchmark, so there's a huge variance. But it is about tools, not about numbers, okay? So don't take it too seriously. But yeah, the truth is similar. Okay, so new JVM doesn't help. But what if I actually take this JVM, graal? That's a huge thing. Now I have numbers which are more or less the same. Immutability in graal, in this particular case, doesn't cost at all. Wow, that's a huge thing. Okay. By the way, I did a little more tests, but I don't have time to now cover everything. But this is something I decided, okay, so we have numbers. Never be satisfied if you have numbers. That number is not an answer. It's the start of adventure. Because now it's interesting. The JVM, like classical ones, OpenJDK, they are not good at immutable class calculator. I say not generally just on this piece of code. I've seen they are not really good. But for some reason, graal is so much better. Why is that? You should answer this question. You should know. If you don't know, then saying just the statement graal is just better is probably misleading. You will just spread something that, again, will be maybe sometimes true, but not always, and people will take us as a truth, but they will then make a stupid even performance mistakes, yeah? So we have to inspect that. And how to inspect the JVM, what's happening? There are tools for that. One of them that you can check is, for instance, Java flight recorder. By the way, I don't think it works on OpenJDK, but it works on Oracle JDK. And there is like a license for that. Basically, it's a commercial thing, but if you do it for development purposes, researchers, you can use it. So what is a Java flight recorder? Is a kind of agent that puts all the meta information about the JVM that potentially are relevant. Some kind of event log that describes what's happening. And okay, there is a complex license. You have to analyze it. You want to use it, but forget it. We don't have time. I'm not a lawyer. So Java flight recorder is a low overhead. That's a very important thing. So it's like it takes events, takes measurements, but doesn't slow you down. So a lot of the times when you debug something, when you do profiling, you will see that your program becomes way slower. So point of a Java flight recorder is it shouldn't make your application visibly slower. It's okay. It depends, but typically it's actually fulfills this promise. So it more or less works the same speed. It means that you can look at the events, recorded times of the functions, and take some assumptions about that. So when I put here like how to enable flight recorder, maybe you will need to call this before. Yeah. So let's say that we've actually run our code with this flight recorder. We recorded this. This will be saved in this myrecondric JFR. And there's the second tool, Java Mission Control, which is basically graphical interface to browse such recordings. And Here on the left part of the screen, I have Java 8 recording. On the right, I have Graal recording. And maybe first thing actually, I haven't shown the menu. There are multiple dashboards here that you can browse, very detailed. I went to the method profiling, and I haven't really seen anything interesting. So there must be a problem in a different place. This is not about Java Mission Control. There are specific talks about Java Mission Control. I recommend you watch it. I just show sooner or later you will go to this screen, which shows memory usage, and you will see that in a JVM 8 there was like huge consumption of a huge operation by garbage collector, like more than gigabyte. And in case of Graal, nothing was happening there. Like there was no actually allocations after some initial start of the project. Okay, interesting. So I might now have a hint what can happen here. Yeah, but maybe you don't have this flight recorder. Maybe you are just have it. The problem, the thing you are measuring happened on a production when you have OpenJDK, something like that. There are additional tools you can use. JPS is simply like you dump which Java processes you have with JVM arguments. But what's the point? You will get these numbers. Those are bits of a Java processes. And if you have this, you can call, for instance, JStack. There are additional ways to do this same, but JStack is just a standard tool. It will print you the stack traces of all the threads on this Java process, which might point you what was actually called at the moment you were running that. In our case of Imu Table Calculator, it won't help much. Same as method profiling. And by the way, now contrary to what Java file recording is doing, this is very sensitive to something called a save point. So basically, when you do a snapshot of all the stack traces, you will never get fully, fully realistic results, because these codes will never stop in some specific place. Basically, whenever you have highly CPU intensive computations, the JVM, okay, the last version, let's say up to 8, wouldn't stop and would just continue this computation and only will print the stack trace after this computation, which means you will never observe some things. Now it's a little bit better with the new versions of JVM, but that's a different thing, yeah? But in this particular case, that wouldn't help you. That is an additional tool called JStat. It's basically statistics. So, for instance, you can connect to existing JVM process, and you can print usage of garbage collection. So this was this kind of calculator I connected, and I've seen that there is constantly something happening on this young generations. And now, in the case of Graal, nothing is happening there. So more or less the same result I've seen in Java Mission Control. So there is some memory usage. For some reason, Graal doesn't really allocate anything. But why? What's happening there? Of course, you can go to answer this really, you would have to go to the description of optimizations Graal does. Particularly, you will find yourself in area called escape analysis, as far as I remember. But you can just go to assembly and see for yourself. So there are those JVM options, which basically all Oracle inherited JVMs have: print assembly and print. And by the way, you never use only this. You must use this basically because there are two syntax of assembly, AT&T and Intel. And if you see for a couple of seconds AT&T syntax of assembly, you will hate assembly to the end of your life, or you can go mad, or lots of things can happen, or you will think that there was a fraud in elections. So a lot of bad things may happen to you. But just look at assembly with an Intel syntax, because it's so much cleaner and more readable, more popular in the books. So yeah, use this. By the way, that's not only this. There is an additional library you have to put into JVM. But if you are looking at JVM, my assumption is, at assembly, my assumption is that you are smart enough to find the DLL or shared library and stuff like that, because it's described in many places on the internet. If not, I can help you because, okay, that's actually a place where you can spend a little time. I just don't want to cover this. I want to show the results, but it's a little bit tricky. Just remember that. So, but finally we'll get something like this. So as before, we had this print compilation. So we had display, we had information when the method was compiled. Now we additionally would have information compiled to what assembly. And when we have that, so let me be honest with you. I can write assembly. I sometimes, okay, very rarely, like once per 2 years, I write assembly code just for fun. Not much, like a weekend, nothing useful, just to have a little bit of fun and see what's like in a modern processors, mostly like that. And still, it doesn't help me. If I am faced with this, and this is incredibly simple assembly, it's hard to find familiar things, especially that you won't see just this, 20, 40 lines. You will see megabytes of output because that's the reality from a real project. So even from this calculator, I just extracted few lines that are interesting because they exactly show immutable calculation test here performed. That's exactly this code, but I had tons of other stuff. And it was even more complex because this immutable calculator was there many times. But what is important here, that this is the jump instruction. This is starting with 0, basic x. Okay, this is, but you have comments which line is this. Okay, I will show you in a moment how it's better. Here is incrementation, so that was our loop. Here is addition, and that's it. So you will see that in our code, now I have some kind of a loop. Actually, okay, I haven't really printed all the code. I have some loop, I have some additions, but I don't have anywhere just a call to new method and allocations. And that's the thing. And by the way, if you write on hand assembly for more or less doing the same, you would end with very similar code. Now it's a little bit more stupid things here happening with registers, but this is almost the same code you would write if you are doing this loop in assembly by hand. Yeah. So this means that Graal was really, really smart to completely, optimize and throw away all these allocations and actually compile this code to the same form as mutable calculator would have. Actually, as normal for loop without any objects would have. Just an incrementation like summation on a long. This is cool. However, looking at it from this perspective on these dumps is very, unpleasant. There's a better tool, Jitwatch, which allows you to, on one screen, see, this is my Java code, this is my byte code, and this is my corresponding assembly, really one-to-one. So Jitwatch actually shows all the stuff. So it's tool, I would say, almost like Java mission control, but it uses dumps from a machine. Not really this flight recorder, but this dumps from assembly and from compilation. And you can analyze your code this way. Now it's way easier to find the stuff, yeah? Where is this add? Where are the loops, etc.? So that's the point. So, and what we can actually now confirm that in the code, in the final code of this method, there is nothing like, so in the bytecode, and that's important, in the bytecode, we have this all new, but the bytecode was changed to assembly that doesn't do any allocation, which is cool, yeah? So if we have some time, I will just show you this. If you don't understand what's happening, I'll try to put it very simple, but this talk originally was for Scala, for a statement that monad transformers are slow. And monad transformers is something even beyond monads, very high, in abstraction levels, yeah? And people know and accept, basically that if you use monad transformers, your code will be very, very slow. It's even slower than, using immutability. Because, for instance, immutability is kind of a default in Scala. And by the way, when I had this code in Scala, it was even better performing than this in Java, but because I could do also immutability on a for loop level. and still the code was fast. Yeah, but this is a different story. So I won't get to the details, but here, let's say I'm doing something. I have some list of users. Some of them I can find, but only optionally, and some of them I cannot find if I find by ID. So this is like typical case for optional. And now with the library Scala Z, I just want to show how it would perform if I use classical approach, having stacked monads. It means task of option. Task is basically there is a future. This will be happening in the future, that there will be optionally an user. So asynchronously, I can get optionally an user. And compared to that will be a code that basically uses monad transformers, and it's a little bit simple but more complex in a way it works. But when we compare the performance, what we see, yes, monad transformers were slower, but not but high margin, not by a high percent. It's not twice as slow in this particular case. So the statement that people present is actually something that is more or less true. I would agree with that, but it is not valid in all the contexts. Yeah. So for this monad transformers, but we are not covered that. Don't go into that. This is a Scala thing. Remember the thing: find user by ID and return optionally an user or something. What if we used null in Scala? Don't use optional. Don't use any asynchronicity. Just use null. How would that be? And now interesting, on the JVM8, it's so much faster. So just not doing any functional programming here, doing just null, it appears to be way, way faster on the JVM8. Yeah, it's a pity actually, but it is the truth. This is a reality. But in reality, we don't typically find user in some collection in memory. What we do, we find them in a database. So let me put the real database to the picture. Let me edit. And now our thing looks like that. That's the context. So, come on, null was faster. Monad transformer was slower. But it doesn't matter if you are already calling the database. This is the huge problem. Maybe you should think about removing the database of the picture, but this is really a point. I see the same in Java and in a Kotlin, that people care about micro optimizations. Don't call it just cache this, I don't know, this call something. When a line later, they process huge table in the database. And at the end, no matter what they do with the performance on a micro scale, they might save 2 cycles, but it wouldn't be measurable actually. So this will be like small person and sometimes really not visible at all. So here I even compared the database with plus monad transaction. Yeah, but nevertheless, solution to that was, if you have the database and you want to make it faster, maybe for instance, there was just something maybe you should use here was a very smart query with a where statement, etc. So solve the problem on SQL level. And now it's interesting how it looks like now. Yeah, optimize the DB solution. So, and that's my goal of this part of the presentation. Look at the problem from your application perspective. Maybe you would have to make the problem smaller. Like, this is my service. This is now called. Like, we call this service 1,000,000 times a day. So what's happening from the start to the end of service? Put that into measurement. Profile that. There are great tools for filing. Monitor that. There are great tools for monitoring, like Dynatrace, JProfile, the tools that can help you and visualize what's happening. And then fix what is really a problem. Maybe, and by the way, quite often we developers assume the database is a problem. This picture confirms that. But my experience shows that quite often not. It's like we like to solve the problem on a database, but sometimes the database is not really guilty, although we like to make it guilty. Yeah? So the point is that we can even go, by the way, here it doesn't really change much if we go to graal. So also interesting. Sometimes we even have to go to deeper than assembly. Okay, I have a couple of minutes still. So for instance, This is now Scala. Sorry, I haven't rewritten that. Scala 4. And by the way, for loop in Scala is not a really for loop. It's more iteration. But nevertheless, it's kind of, we have two-dimensional array. And we do a classical task that you will see on many conferences when they describe you how CPU works. This is a classical example. And in Scala, basically, to be more low level, you don't use for, you just use while loop. And again, I just go row by row, I add something from this array, and then produce result. You see, JMH also works with Scala a little bit differently. That is our corresponding black hole. If you return something, it goes to the black hole. But then we do something else. We transpose while and reverse. So we go backwards, and we go column-wise. So instead of reading row by row, we just go column by column. And you will see this example multiple times on the presentation, that it is way slower to do that because of the caches. And how can you measure that? You start JProfiler, but with these parameters, prof. And by the way, again, you will have to install additional program on your machine, maybe some additional packages for your kernel, but it will work. It will present you some numbers. And yes, as other talks show, while with transposed and reversed like walkthrough was actually slower. So while was the fastest, for because of the Scala 4 is written was a little bit slower, but this while was the slowest. Yeah, and then you will have a lesson about latencies of caches of CPU, that if you go byte by byte, the things land in the cache and are very fast read from the cache. And this is actually optimal approach for reading stuff into dimensional arrays, go row by row. And then you can, this is exactly JMS hprof thing. And here is the thing loading from L1 cache. This is exactly this transpose. We've seen so many loads and almost 70% of cache misses. Compared to the standard solution, where normal while, where there were only 12%, like 13% of cache misses. So we see that because of cache misses, one is better than another. This is a classical thing. But now, funny story. I recently read, I couldn't confirm that the new Intel processors actually will be able to find out this pattern and optimize it for you. So maybe, and I'm talking about Xeon processors. I couldn't confirm that in the documentation. This is, let's say, this is just a gossip. But maybe there is some truth in that. So I haven't this kind of processor, so I couldn't confirm. But maybe in 2 years, someone will be presenting this classical example, and then you will open your laptop and show that there is no difference. That will be a huge thing, yeah? Because CPUs are becoming faster. Then they see that a lot of us, just because of some reasons we wanted to iterate in a different way, and then can optimize that for us. So I haven't covered in this talk garbage collector problems as ahead of time compilation, tons of JVM options actually that you can use to inspect more what's happening, or even tune your just-in-time compilation and stuff like that. Because this is a huge topic. The benchmark I presented in numbers were lies, so I presented numbers as on my machine, but I never really cared to really isolate this machine, etc., etc. And always assume that most of the benchmarks are more or less done unprofessionally, or there is some unfair thing when you compare done unintentionally even by the authors. What I wanted to show you were the tools. So when you see a benchmark that if you see some numbers, ignore them unless you can prove them on your own, because there is a source code. You read about libraries that are used. So for instance, so that you know that you not misuse the library. I remember 20 years ago, someone showed me we don't use prepared statements because they are way slower. And by the way, reality is that in most cases, they are not faster, they are not slower, they are more or less the normal statement in JDBC. But if you do really broken benchmark, they will show as way slower. And that's like really, you have to analyze and look, if you compare two solutions, you have to read a little bit how they work, what are bad and good practices, so that you really compare them fairly. And finally, a benchmark that the result you can put like, this is a guide for me. I will use that in this critical piece of code because it's faster. And I know why it's faster because I've analyzed the differences. No, like it is faster by 30%, but who knows why? If you know the difference, you can prepare yourself for the future. So for instance, you will know that maybe in the new JVM, it's just because there is a bug in JVM. I had such examples. Like it's a bug in JVM, will be fixed in the new version. Does it make sense to make your code less clean just to, while you wait for a new JVM version, which will be maybe released in a month or two? And then this bad code will stay. So this was talk not about numbers, not about that much functional programming, but about tools that these tools typically I don't use in my daily business. I use them mostly in problem solving. I involve them, I actually present some benchmark I have on my GitHub, mostly when someone says me this generic statement, and I want to show, oh no, that's not actually always true. That's sometimes true, and see for yourself, yeah? That's how I produce most of the benchmark, just to prove that someone is wrong on the internet, yeah? But if you know these tools, you feel more comfortable because so I try this in free time, even if you don't need it, because when you will need it, you won't have time to learn how JProfiler, okay, I haven't shown the professional tools like JProfilers. You will never have time to learn it when there is a real production problem with a performance, yeah? So you have to be prepared upfront. And better try on your, pet system that you can really heavily inspect and debug than on the real production, which is always more complex, yeah? So real maybe problems I had on the production, I still remember my lesson from when I was a junior, when I seen a very, very complex code written like, in Java, that was Java, but written like a low-level C with byte manipulation, byte shifts and bit shifts and stuff like that. It was really horrible to read. And the funny thing is the developer of this piece of code haven't realized that whilst fighting so much for cycles, he's accidentally reading a whole database table. It's really, this is for me a really typical case of how someone fighting for cycles becomes so defocused that he is doing a huge performance error. And then this code was such a nightmare that it wasn't really visible. A really simple thing is synchronize. So locking. I had multiple times static method synchronize, which was even a static method for just put some lock information into the file. But it was, because it was used through all the system, it was slowing it extremely, like all the time, even on a huge machine, there was only one thread actually working. That was an interesting lesson. Yeah, and so, but nevertheless, always when you see something, many times I said, oh, I found static synchronize. This slows down this system. So I remove this synchronize, I rewrite the code so that's still safe without synchronize, and bam, there's no difference. Be prepared for that. That's why we have benchmarks that we want the repetitive numbers, because we repeat and we see if our solution really fixes the problem. Yeah. Hashcode equals bugs, so where hashcode equals are very written in a bad way, inconsistent. That leads to a lot of funny performance problems, which are sometimes only observable on huge data sets on production. JVM problems, bugs with meta-space garbage collectors, that's something that I've observed a few times. And that's particular a problem because sometimes you have to do a huge workaround and even change the architecture of your system. We had this case. And locks, deadlocks, basically. So actually the problem is that the system performs very slowly, but if you analyze, there is no I/O, no CPU, nothing is happening. You have cluster of F machines that are doing nothing, and the system is slow because there is some kind of a cluster lock. That's a typical case, yeah. And in many of those cases, that's the thing that people that do performance audits also confirm. Many of these problems can be just spotted by using JStack, even though JStack is not perfect because it has some potential problems that will not show you anything. Remember the save point problem that's discussed on other talks, yeah? So this is so. This is the end of this talk. remember that, we are talking about changing world. Things that are now slow might be faster in the future. So be careful when you make a huge statement generic, because it might be not true in the future. Because compilers and CPUs are designed to perform human readable code actually faster. So they analyze what we as humans write typically, not as a hacker's code, but typically, and make these patterns faster. Yeah. And last but not least, it's like, okay, it's not even the last, like, you don't concentrate on micro benchmark, concentrate on the things significant from the system point of view. So like if you have a service that's heavily used, measure what's happening in this whole service. Don't concentrate that one construct is slower, because maybe it's slower, maybe it's 100 times slower, but it's once called and it's different between 1 nanosecond and 100 nanoseconds, doesn't really make a difference for the whole system point of view. And because of caches, quite often it's absolutely not measurable. Yeah. So, and at the end, if you are presenting some code and someone says to you, "Oh, you have to rewrite it because it's crazy. It's nice, functional code, clean, but it will be slow because you have to do loops." You have to ask, do you have really benchmarks of that? Can you prove me that it's important for the speed of our system? Like, ask this question, because mostly people that will bother you about performance, they don't measure anything. They are just repeating generic statements, which are mostly not true. Yeah. So thank you. And yeah, I will be in a Q&A session ready to answer more details. Yeah. I have more code if you want.
Thank you. Thank you, Jarek. Thank you for joining our event today, and thank you for 2 talks you conducted. Dear participants, please join Q&A Zoom rooms with Jarek, and he will answer your questions on both talks, first and second. And Jarek, I hope we see each other next year and the lockdown will be ended by the time of the next Devoxx, and we will be welcoming you in Ukraine.
I definitely miss Ukraine. I'd gladly be there. Yeah. So thank you.
Thank you so much.